Good morning, everyone, for today's distinguished webinar series in AI and cybersecurity. Today's distinguished speaker is Dr. David Oswald, full professor in cybersecurity, Department of Computer Science, Durham University, UK. The title for the presentation is From Paperclip to Interposer, Memory Aliasing Attacks on Confidential Computing. Dr. David's research is in the security of embedded systems and trusted execution. His work includes the practical realization of security systems and, more recently, analysis of trusted execution technologies like Intel SGX, TDX, and AMD SEV-SNP, as well as applications of CHERI in this context as part of the Digital Security by Design initiative. He has numerous papers in top-tier venues such as TCHES, IEEE S&P, ACM CCS, and Usenix Security. He is also the PCs of major conferences, including Usenix Security, TCHES, and ACM CCS, and was a general chair for CARDIS 2022 and CHERITech 2024. Dr. David, it's a great honor to have you on board for this morning. I appreciate you being with us, and the floor is yours. You have about 40-45 minutes for your talk, and then we have open for question sessions for the remainder of the session.
Good, yeah. Thanks for coming here. So you had the pleasure to read out all these acronyms like TDX and SEV-SNP and so on. So I'll try to shed a bit light on what is behind these acronyms as well. So the initial question is, if you use the cloud, which is very likely, even more these days, because you cannot run like these huge frontier models on your local machine unless you have a data center, which I heard there are now a lot built in North Dakota, by the way. So you can look that up. So you have to trust your cloud provider to some extent. And we want to, ideally minimize that trust. Now, if you look through the news, you will find all this kind of headlines that the cloud is not unbreakable. You have various security breaches. Oracle had problems recently. For instance, like a major software system that is used by a lot of universities for their student data was broken. Canvas, you might have seen that. So they had like a major ransomware problem where lots of student data and student information was stolen. So one answer is we just do what we have been doing, right? We improve software security and put people with guns in front of the data center to prevent physical attacks and so on. That is quite costly and will never solve everything. So we have like alternative or additional solutions, and one of them is called confidential computing. So the idea is to create another ring in the CPU if you want. That is often called a trusted execution environment or an enclave, or these days a confidential virtual machine or CVM. And these execute at a privilege level above the hypervisor or the operating system. So even if your adversary has obtained root access on the cloud server, then the data in this confidential computing environment are still protected. And here come all the acronyms. Every major vendor has a system like this or multiple systems these days. Intel has SGX and TDX. AMD has SEV with various other acronyms at the end for the evolution of that. And ARM has a Trust Zone, which is probably in every Android mobile phone, and the newer variant that is called CCA. So these provide interesting security guarantees, and sometimes they even claimed in different contexts that they prevent against an attacker who has physical access to a server or a machine that runs these environments. So the way that works these days is often that you work on the basis of VMs, like containers or VMs. So in a classical VM system, the hypervisor can read the memory and write the memory of any VM under the hypervisor. So if the hypervisor is under control of the cloud operator, then it can, by design, read out your data. In confidential computing, we modify the hardware a bit to add additional levels of access control, isolation, and a function also called attestation, so that the hypervisor can no longer access anything inside this confidential VM. And further, you can also attest to the fact that this actually runs on trusted hardware, like built by Intel or AMD or ARM or so. So you said that the seminar is also about AI. if you have used WhatsApp recently, which I guess many people do, there's now this funky AI functionality in WhatsApp, and that relies heavily on confidential computing technology, in this case, the SEV-SNP technology, to make sure that WhatsApp or Meta can feed all your messages into like large language models to summarize them or whatever, without uploading all your data in clear text into their cloud. So this technology becomes very mainstream with the need to run large models. So today I look at it from a quite low-level perspective, and I look at the perspective of a typical how a server is typically built. This is a motherboard of one of the systems that we use. So you have like the CPU where this trusted execution environment lives, and you have like a BMC chip that controls the power state. You have a voltage regulator. All these components can create attack surface. But in this talk, we focus on RAM, which is kind of semi-trusted, as you'll understand during this talk, by these confidential computing environments. So just to give you a bit more of an analogy, this is Durham, where I'm just sitting. So if I look out of the window here, I can nearly see this castle. It's 1,000 years old. It's also used as a student dorm. So you can imagine that all the students want to live there, because who wouldn't want to live in a castle? Anyway, the function of a castle is a bit like this trusted execution. So you have very high walls. And when the trust boundary of the city has been broken, then the castle is still kind of secure, right? Now, as you also know, if you have looked a bit at history, there are various ways to break into castles. I won't go through all of them, but one very old one is to kind of like make some piece of the castle misbehave, or like of the infrastructure around it, basically like a Trojan horse, right? So the whole idea of everything in this talk is to study if we make the memory misbehave, if we change the behavior of DRAM memory from what the CPU expects, can we break this kind of confidential computing systems? So you will see a lot of attacks in this talk. And the answer is positive. We can do that. And you will see kind of like now a whole line of work about how that is possible. So to give you, without too much detail, to give you a nutshell understanding of how this confidential computing actually achieves security, one very important ingredient without which it cannot function is some form of memory protection. So even when you root in the normal operating system, some area of memory, of DRAM, is blocked from your view. So if you do like an access into physical memory as root or hypervisor, and that falls outside this trusted execution environment or CVM, then the access will pass. And if not, if you try to index inside the TE, then this will be blocked at the hardware level. So there are various instantiations that might cause like an exception, or it might just return zeros or like some fixed value or something. An additional ingredient on top of that is that also all memory is encrypted in modern servers on the fly. So it uses typically these days some variant of or some operation mode of AES to prevent somebody who has physical access to the memory, for instance, by tapping into the data bus, also to actually make sense of the memory contents. And now, depending on also the variant of trusted execution environment, there's sometimes authentication on top of that, and there's even replay protection, so that you cannot replay old ciphertext at a different point in time. So our idea was quite simple. The way that that this works, this whole design is, you get a physical address out of the CPU, and then it will compare that in the memory controller or somewhere to like the TE range. And if it's within the range, then it will reject it. So our idea was, can we create a ghost address that looks to the memory controller different, but aliases into this trusted execution environment? So in other words, can we have two addresses, two physical addresses, two memory addresses, point to the same location on the actual DRAM chip? And this is where the first half of the title of this talk comes from. It's what we call the paperclip attack, a very early proof of concept. We did this on DDR3, and on DDR3, it is of limited impact because there's no trusted execution environments that actually uses DDR3 memory, or no interesting modern one at least. And here's the infamous paperclip. So if you look closely at this image, you see like a DIMM memory module and a little paperclip wire sticking out of the slot. So what this actually does is it pulls one of the address pins of the memory module physically to ground. Now, even if the CPU tries to pull this high, this 14th bit of the address, the memory will still return the value from A14 set to 0. So in other words, you have like the memory. Let's kind of imagine it split in two halves. And now our paperclip comes along. What this will mean is like an access into this upper area of memory will actually alias into the lower half of memory. So the CPU will see like the top bit of the address being set, but actually really it returns the value of the lower half of memory. So that is an interesting attack primitive, and we tried that it worked on DDR3, but as I said, there's no way to actually target an interesting confidential computing environment on DDR3. So we thought long and hard. We tried a bit doing paperclips on DDR4. That's not quite as easy as I'll later explain, but then we found there's actually an easier way. Our idea was maybe we can turn this around, and instead of kind of pulling one bit low, can we maybe make the memory appear larger than it is, and this way create aliases? So you might have, if you ever bought like a cheap knockoff USB from some online retail platform, you might have encountered situations that you bought like a 1 TB USB stick, but actually it's only 128 gigabyte physically in size, and just wrong configuration data is returned. And that's exactly what we're doing here. So on the cheap knockoff USB, if you write into the upper half, you'll probably corrupt some data structure in the lower half of memory, or something else bad might happen. So the equivalent of the configuration data in DDR4s, which are more interesting because, for instance, this AMD technology uses DDR4s or Intel SGX. We figured out that memory like these DIMMs, these memory modules, are actually quite dumb. So the memory chips themselves just have address inputs and they have a fixed size and so on. But the address inputs, the number of them is the same for any size. And if you kind of like toggle bits or address bits that are actually outside the size of the DIMM, it will be just ignored. Now you have multiple of these memory elements, and then you have a little EEPROM chip that stores all this memory configuration, including the size. So this is called SPD. SPD is used at boot up by the BIOS to configure how much memory you actually have. And in the fifth byte, basically, it encodes how large this module is. So what we thought is maybe we can just emulate during boot the contents of this chip and return a wrong size. So we have like say a 16 gigabyte DIMM, and we say 32 gig in size. So it's level one. So we built like a little Raspberry Pi based setup where we desoldered the memory, like this little storage chip, this little EEPROM chip, and emulated everything. But then we actually figured out that this is a bit of overkill to do, because you can reprogram the memory chip that is on the DIMM. To do that, you often, and I'll come back to that a bit later, need to deactivate some write protection. So you need to apply a high voltage, relatively high voltage for embedded systems like 10 volts or something to a certain pin, and then you can unlock this memory module. So that requires brief physical access. You typically cannot do this in circuit. And once you have that, that's our final evolution of the setup. You can all package that nicely in a little Raspberry Pi Pico with a bit of wire and a memory slot, and then you can kind of reflash these SPD chips on the fly. So what does that do? Let's say we have a DIMM that is actually 4 gigabyte in size. So that's how many bits are on it. And we just, with our primitives that is called batch RAM for obvious reasons, I think, we can reconfigure it to be or to appear to the system to be 8 GB in size. So what will now happen is if we do an access into this upper half of memory, there's no backing memory there, the DIMM will just silently ignore that, and the actual access will happen somewhere down here. So this access at 4 GB plus something goes to 0 plus something. So now repeat that with the trusted execution environment in here. So let's say it lives somewhere down there. If we were to do a direct access to a physical address inside this TE, I would just get rejected, obviously, by the access control. So what we do is instead we access the aliased address, which is somewhere in higher memory that doesn't really exist. The CPU will say, this is fine. I'll allow the access because it's outside the TE, obviously. But the actual access will alias down into the TE memory. So suddenly you have like a way to read and write the memory that backs this trusted execution environment, which is the thing that is normally prevented by the CPU architecture. And it's all in all like a very low cost method, I would say, because you just need like a little 5-pound Raspberry Pi Pico to reflash the memory module. So that might happen while the module is shipped to you, or it might happen when somebody has brief physical access maybe when a physical adversary is in scope. So we tried that first with the old Intel SGX trusted execution environment. That has actually, of all the things we looked at, the strongest cryptographic design, because not only is this memory that we can now read and write encrypted, but it also is authenticated and has freshness protection with counters and a whole Merkle tree that authenticates everything that is all these counters. So if you do any write via such an alias, you essentially the system will go down, so you cannot exploit it. The downside and why this design is actually no longer used is that the memory is extremely limited. So in classic SGX, you started with a maximum TE size of 256 megabyte, and it got a bit bigger, but definitely not large enough to hold like large LLMs or something. So hence all the newer systems are actually surprisingly and counterintuitively a bit weaker in their memory encryption. We can still read encrypted memory, and we can see the encrypted memory changing. So that gives us a primitive that previously in a 2020 Usenix paper required a 170K piece of test equipment called a memory interposer. So we do not do any changes. So the freshness and the Merkle tree and so on are not affected. We just run through memory and see if it changes. And that might give you some information if there's like, for instance, some secret encoded in the way memory is accessed. So was a good start, but maybe not the most motivating one. But luckily, we then could move to the newer designs. So as I said, these newer TE designs do not guarantee freshness, and that's a pure performance and size trade-off. So for instance, AMD SEV-SNP, memory is just encrypted, but there's no authentication on it, and there's no freshness protection. And in addition, there's like a memory range access protection. So just for reference, the way that works is it uses AES in a mode that is similar to disk encryption, if you ever looked at that, where you have an address-based tweak that is XORed on whatever is in plain text in the memories, and it goes through AES. And then the tweak is XORed on it again, and then you get like the encrypted memory content. So it's quite a common way to do encryption for like blocked devices, essentially. Here, one thing to note, if you take a memory block from one address and put it in another address, this tweak will change. So you cannot really like just paste memory easily somewhere else and decrypt. If you want to do that, you need to be careful about this tweak. And we come back to that in a little while. So looking now at SEV, there's a critical data structure called the RMP. And we found indeed that with Batram, we can simply alias into that and could build all kinds of attacks if we wanted to. However, we can also read and write encrypted memory via an alias. So what this allows us to do is we can not change the location, but we can replay an old value into a specific location. So the way that works is you do a read by an alias, and you let the enclave or the TE progress a bit, and then you write the old value back to the alias, and then suddenly a variable will go back in time. You can imagine, for instance, if you have like a variable that says a user ID, let's say that starts out at 0, which means root, and then it's later changed to like a lower privilege, then you can later during the execution simply replay the content of that variable and switch back to root. And indeed, we built some exploits on top of that. So here's an example. On the left-hand side, you have the VM, and on the right-hand side is the attacker program that has these access to these aliases. So I'll play the video in a second. Now, what on the left-hand side, we have a buffer that sits at some address that is initialized to 0. Now we can capture the ciphertext from the attacker. And so here's the ciphertext of the 0 encrypted at a certain memory location, and we can just store that. Now inside the VM, we change the whole buffer to all F. And after that, we'll just replay now again this value we captured previously, and then we'll read it again in the confidential VM for demonstration purposes. So now we replay on the right side. So we have replayed that. And now on the left-hand side, when we read this value again, it should be all F still, but we have actually reset it to 0. So we have state restoration attacks that you can build. And you can imagine if these confidential VMs, they run complicated programs, they run standard binaries, things like the Linux kernel, etc. So you can build all kinds of exploits on the basis of the state restoration. What's more, we could actually also bypass this attestation functionality, which allows the system to prove to a remote entity, for instance, to your phone running WhatsApp, that it's actually running in a confidential VM. And the way that works is that the VM at some point hashes its own contents, and then a signed version of that is sent to the other party. And what we can do is we can run a valid VM, capture this hash, then modify the VM to our liking, and via an alias replay the hash of the unmodified VM, and then break attestation in that way. So AMD was worried enough about that they rolled out a firmware update. And this firmware update is a so-called alias check mitigation that we'll look at in a second. It's, by the way, something that Intel, when we did this aliasing attacks, had already implemented. So in this case, Intel, at least their newer SGX versions were better secured. They are the kids. So before I, however, go to this, I want to talk a bit about the adversary model and how this might be a software or hardware attack. So we got us a bunch of memory modules back when we did this work, and in most cases we required hardware access to do these changes to SPD memory. But if you look at top, there are two gaming DIMMs that were actually unlocked. So in this case, you could have done a software only attack. And I'll talk about that in a second a bit more. Luckily, this work was done before the huge AI boom, so DIMMs were actually achievable. And now we can pretty much retire just by selling these. So talking about other attack contexts, this was all confidential computing, but I want to go a bit wider. So first of all, we also looked at ARM. There's no protection against aliasing in the trusted firmware, and ARM considers this out of scope. So what you can build with that is the user mode 2 trust zone privilege escalation exploit. And that will be presented at Root this year. And secondly, we also looked a bit deeper at these gaming DIMMs and thought about, well, where do people do gaming? It's typically Windows. And we got ourselves more gaming DIMMs, found that many are actually unlocked. And further, that in Windows, there's a way to change this SPD configuration from software. So why is this interesting? It's not like this TE. Well, Windows actually uses also some form of trusted execution to boot its kernel. There's something called virtualization-based security that underlies something like, in the end, like Defender for virus scanning and all these endpoint security technologies. So in combination with these gaming DIMMs and the software access, you could also actually completely bypass that and build like a quite powerful software attack that bypasses all kinds of antivirus protections, etc. So this is a paper that is coming out at Usenix this year. Good. Coming back to confidential computing a bit more. This is what this SPD aliasing could achieve. So we could completely break SEV-SNP. We could not do much for classic SGX because it's very strong crypto memory encryption. The newer things from Intel, scalable SGX and TDX, have this alias check on boot. And what that will do is it scans memory during boot for aliases. If it finds any, it will not enable SGX or TDX. So they actually thought about this vulnerability. Which makes, like, for the attacker, raises an interesting question. If something is checked at boot time, can we maybe just do the attack a little bit later after this check has passed? So we're here in the scenario of a time of check, time of use attack, essentially. So when a server comes up, the BIOS starts, it will read the SPD, it will train the memory, and it will then perform in this boot flow, both on Intel and AMD machines now, and on AMD after our patch, an alias check, which essentially just does like a few memory accesses into maybe the higher half of memory and then checks if there are any changes in the lower half. So you can be quite efficient about this. And then if that passes, the system will be configured, and much later you can start the TE. So can we maybe do something like basically a paperclip on the data bus, on the DRAM bus, that we only enable after the check has passed? So I mentioned a bit before, there are actually commercial devices to do this kind of stuff. They're called interposers. The thing with them is they're not particularly cheap. So this is, for instance, one. Can buy one from Keysight. It's only 700 grand. You can get cheaper ones. There's some other work from Daniel Genkin's group in the US who found like a very cheap, relatively cheap one of them on eBay. And then you have to deal with like first upgrades, the interposer from Windows 95 to Windows 98 and this kind of stuff. Yeah. So we thought this is not so great, right? So to just like throw a lot of money at it, and then somebody will say this attack is not realistic because nobody has this amount of money. So what we instead did is we tried to find what a minimal cheap memory interposer needs. And this is the subsequent battering RAM attack. So here's our server again, and you see there's like on the DIMM behind here, there's like a little red module stuck between the actual DIMM and the server. You see a few like little switch modules down there, and our Raspberry Pi Pico for controlling them on the top. So this whole thing costs like in BOM cost a few $10 or something. It's really cheap to build, so no 700 grand anymore. And what this does is it is essentially a virtual paperclip or like an electronic paperclip, with the difference that we don't have to fiddle with the live computer, but it can kind of like switch stuff around and does some more interesting things as well. So here's the interposer. So on a DDR4, it's a bit more complicated. You cannot switch the top bit around. You can, however, switch bit 13 around. That's due to the multiplexing on the DRAM bus here. So at boot time, you see this switch of A13 is just passed through. It's like if you have done a bit of electronics at some point, it's like an analog switch, which is like a relay in a way. So it will pass through any signal if a control line is set in a certain way, and otherwise it will just pull the pin to ground. So at boot time, we disable it, and there's really not any way you notice that this interposer is present because memory controllers these days, they're really reliable. So they do a lot of training and they will compensate for the few centimeters of extra trace length on this interposer board. Funny enough, in later work, we actually looked a bit at if you can see it in the memory training data, and there's indeed some way to see it. But yes, it's not like anything you would normally look at. Then at attack time, the switch will flip, and from the perspective of the CPU, nothing changes. From the perspective of the memory, now the 13th address bit is set to 0. So you suddenly again have this aliases into memory. They're now a bit more complicated because you don't do this with the highest bit, but with a lower bit. So you have like aliases that are a bit closer together. So you have to deal with that. So we tried that out on the newer SGX variants and also on the patched SEV. And it turns out, yes, the system will not obviously notice that this interposer has been installed. And you can just, at attack time, create aliases for a very short time. So on SGX now, which uses a very similar encryption system as SEV-SNP, no freshness or anything. What you can do now is the following. So you have in the enclave, so the blue is here the enclave. Yeah? You have some secret data, and this is in memory encrypted to 3D, 9C, 5D, 95, whatever, like some opaque value essentially. So now you allocate attacker-controlled enclave somewhere, another one, which you need for certain technical reasons, that you place in memory in such a way that when you activate the interposer, the location highlighted in red here will alias to the location where the victim enclave stores its encrypted data. So now at this point, yeah, the interposer is briefly activated. Now the attacker, the red part, will read that value. Now, important to note, it will not get back the secret data. And why is that? Well, the CPU sees the wrong tweak for this address, right? It will see the tweak that belongs to the address that is currently not visible here, but it doesn't use the tweak for the alias address. So you get some garbage out of the decryption. So you don't get secret data, but you get out 2B, F9, whatever, some other opaque value that is the decryption of under the above address of this data. Now you disable the interposer again, and you deallocate the victim. So you kill the victim enclave. Now the adversary will create yet another enclave, their own enclave, to finally decrypt this data in the place where the victim lived. So you see, because we have like root privileges on the system, can do all the shenanigans and place stuff very, very carefully in memory. So now we turn on the interposer and write back to this location the value we captured from the victim. So due to the properties of this encryption now, it will result in the same value that the victim had encrypted in memory at this place. And then the attacker enclave, finally the second attacker enclave, can read the value back and get the secret out. So this is quite like a confusing setup because it involves like essentially like two areas of memory controlled by the attacker. But the idea is quite simple. Yeah, so you capture the value of the victim, you kill the victim, you allocate your own enclave in the space, and then you write the captured value back and get the secret. It's a bit like back and forth, a bit more aliasing that you have to do really. And if you now package this all nicely in a library, then you get arbitrary plaintext read and write access to any SGX enclave, and same in SEV-SNP. So let's look at a little demo here. So we start the application with the aliases. And actually here we target a specific victim enclave, which has a very important role within SGX, within the SGX ecosystem. The provisioning enclave, or PCE, which basically deals with all this attestation. So this stores a very important key pair that is used for attestation. And now we'll basically dump the memory backing this key pair. So we call this victim. We now enable the interposer, which is really like a manual process. So we stop the victim at some point. And we get the victim's ciphertext. That is now stored. Now we switch off the interposer. Sorry, try to go back there. We switch off the interposer. We deallocate the victim, this PCE enclave. We create the read enclave by the attacker. Then we enable again the interposer, store back the old ciphertext we got from the PCE enclave. Switch off interposer again. And then finally, we get like this stack dump of this PCE. You can see here like key DER, which is some encoding format that the private key is stored in. And then finally, at the end, with a bit of Python, we pass out the provisioning key out of that, which is a very, very important secret in which all the security of SGX is rooted. Notably, actually, you can also do this while the server is shipped. So you could kind of like with an interposer do this to the server while it's been shipped, get this PCE out, then continue shipping the server to the victim. And unless they perform a relatively specific factory reset of SGX, they would not notice that their key has been leaked. So this platform would be compromised until they do like this obscure SGX factory reset that nobody normally would have done before this work. So I'm nearly at the end. We're also at about 40 minutes now. So we have some time for questions. I just summarize this all a bit and also give you an outlook on the industry perspective on that. So this battering RAM attack allowed us to do the same aliasing attack with a piece of hardware now. It costs about $50 or so. It's a cheap interposer and an open source design, and it will bypass any boot time alias check. So you can very dynamically switch this around. It gives you arbitrary plaintext read and write on scalable SGX, which ultimately also breaks all the attestation functionality. You can also break SEV-SNP attestation in basically the same way as you could do with the software-based aliasing, the SPD attack. So the message here is hardware attacks on the memory bus are actually not as expensive as everyone thought they would be. You don't need like a super high-end interposer. You can get away with much, much cheaper equipment, to the point where people start to somehow care about this. The limitations of this work is that there is no TDX attack yet because TDX doesn't exist with DDR4. It's a DDR5 only technology. So that's a bit of an additional engineering challenge to overcome due to the relatively big differences in design between DDR4 and DDR5. So what do the vendors of this technology say? So what do, for instance, people like Intel say? I think they give like quite a nuanced and good answer, which is summarized by this talk, actually, that Simon Johnson, who is one of the Intel people behind SGX and TDX, gave recently. So the talk is called Memory Interposer Attacks Out of Scope, but Not Out of Mind. So let's unpack that for a second. Out of scope, yes. If you look at the formal SGX and TDX and SEV threat model, it will say, if you can open the case of the server, the whole thing is completely insecure. So that is kind of like the reality. And the when if an insurance policy or if somebody would look to sue somebody, and I would say like, look here, it's written down. This can only do so much. But still, Intel and AMD and everyone else cares about this because the whole point is to reduce the trust in the data center operator. So they're trying to find solutions that mitigate this to some extent. So we'll hopefully see some developments in that space. However, yeah, as the name or as the title suggests, it's not really in scope. So this will like not be never be 100% like everything in security, but will hopefully kind of further improve this technology. And I guess there's like a good role to play for academia to challenge these attacker models and find interesting creative ways of overcoming them. And then we learn how the systems work actually. So there's been a lot of support and a lot of co-authors behind this work, which I've listed all here on this slide. And I think with that, I'll come to an end after about 40 minutes. And thank you for your attention. And then we have a good amount of time for questions.
Thank you so much, Dr. David. Fantastic presentation. And of course, 700,000 interposer, we don't have academia, don't have this money to
But
explore all.
some people had like the 170K for the older one. So
Okay, cool. Now we open for Q&A, so folks can either ask or pose your questions. Who wants to start? We have about 18 folks here. Any first folks have any questions to start with? We have Dr. Jinlu, I know study faculty also joining here. So maybe I'll start with the first question. Is it easy? And this is not my area, so forgive me my ignorance on this area. But I think locations of trusted execution environment, is it known, or is it actually can be identified? Is it a simple way to know where the TE addresses are?
okay, yes. So normally it's easy, yes, because the way these are constructed is that the whole loading process of an enclave or CVM or whatever is under software control. So for instance, in SGX, the normal operating system first allocates a memory buffer and says like, this is where the enclave is. And then the hands it off to the hardware. And from there, it will be kind of removed from view at like a higher abstraction model. So you can choose where the enclave lives. Not only do you know where it is, but you even can control where it is.
Sure. And then you mentioned guarantee freshness. What do you mean by that, defining freshness?
So freshness means that if you so you have some encrypted memory content, you take it at one time point, then the enclave will change that itself. And then you later replay back the old value that you captured before, then freshness would guarantee that this doesn't work. So that's like a counter on like a version number. So the variable has like a content and a version number that goes up. So let's say you get value 42 at version 1, then the enclaves updates that to 67 at version 2, and then you try to write back 42 at version 1. Then at this point, the freshness protection would say, no, you can't write that back, or I'll crash, or I'll go into an exception handler or something.
Super. We have a question coming in. Leslie is asking, based on the attack you have shown, do you think future mitigation work will need to focus on ongoing alias checks rather than just checking at the boot?
So that's one good question. There's something called memory scrubbing, which is a bit similar already. So that iterates over memory, kind of like it's for error correction for ECC and checks for errors or something. So that would make it definitely harder. However, it depends then on the frequency you can achieve that with and where it's controlled. So if you like would use all the spare memory cycles to continuously scan for aliases, you would probably waste a bit of energy, but you would make it much harder to do these attacks. It would be probabilistic in nature because you might be able to just switch the interposer on very quickly and try to optimize into the time where actually this check is not happening. But yes, there would be a way you could, it would definitely make it harder to run this. Yes.
Is alias checking is a word that your group came up with, or something that's standard in the literature? I'm just curious to
Um,
know what the language.
I think it's like a word everyone comes up with when they think about aliases. But I
Uh-huh.
think as I said, Intel thought about this before us. So they did have this alias check module in there, and it's called alias check. So,
Hmm.
I think everyone comes says alias check
Sure.
directly.
And then with the advent of all these large language models, AI getting attention, the other question is maybe related to how do you see this? From a how do you see the large language models and AI taking shape and actually exploiting these hardware-based attacks? What about side channel attacks, or other things that these LLMs can, from both an attacker point of view, from a defender point of view? Do you have any insight that what could be researchers should be looking at in an academic setting to explore some open-ended problems that we can do, whether this TDX, DDR5, or
Mhm.
as we go along? Any insight on?
So maybe first on the attack side. So like a lot of these attacks are, or part of these attacks is to actually carefully read the documentation. And what made it difficult in the past is that the documentation is extensive. So when you look at the data sheet or like at the Intel reference manual, it's over volumes and volumes, over thousands of pages. So if you can define what you're actually looking for, an LLM would be a very good filter, I think, for that. To search for kind of like these gaps in the low-level hardware. It's a bit similar to payment standards or mobile phone standards. So they're also like a long time they were a bit. One of their protections was obscurity in the complexity. And I think there an LLM can well pattern match on certain things that you're looking for. That might be an interesting area. I know there's some work in hardware vulnerabilities, like feeding a lot of VHDL or Verilog into LLMs and trying to reproduce vulnerabilities. I think it's so very difficult because you need to be really careful when you do academic work if something was not yet in the training data.
Yeah.
So,
Mhm.
so the yeah.
Now we have a big buzz in all these funding agencies on agentic AI, and trying to figure out to see what how do we how do
Um,
we handle that?
And
Yeah.
then in terms of hardening, well, sometimes you have to in this maybe outside the aliasing, but in this you have like additional things you have to take into account. For instance, if in a normal system, if you don't write your code in a branch-free way, it's mostly fine, right? Because the attacker has like limited capabilities. But if you have this very powerful attacker that sits just on the same CPU outside the TE, they can observe every branch decision, caches, etc. So I think it would help probably in finding these kind of vulnerabilities and fixing them. And once you stick like a whole virtual machine into like this TE, you make the trusted computing base quite large. So any security fix you do on the software side is also very helpful.
Another thing you talked about is, are we thinking about performing alias check at different steps? You talked about inserting during this memory training and system configuration phase, but not during the time of use. So, is there a cost associated to actually to do this multiple checks? If so,
Of course,
What are the trade-offs that one should look at? When we.
I think the cost is you do more. So ideally, you don't want to do lots of memory accesses because memory accesses are expensive, right? So you want to ideally you have everything coming out of cache or something, and you don't do that many memory accesses. Now, if you run like whatever an LLM or something inside this, it will never fit in cache. So you will by design do tons of RAM read accesses. So now if you reuse some of them to check for aliases, your performance will suffer at some point. It might be minimal. You can maybe sneak in one every thousands read or something, and then you have like you waste a bit of bandwidth there. But then also the attacker probably has like a larger window, so it's quite a
Sure.
clear trade-off between this checking and performance. So if you do it frequently, it will be quite secure. but also quite, yeah, will cost you bandwidth.
Sure. And then during your another slide on interposer between DRAM and CPU, you talked about dynamically switching to ground during an active case. What does it mean when you say dynamically switching to ground for
Okay.
active? Is it
Okay.
happening all the time, or I'm just curious as to how is it switching? Is it just you're manually connecting to ground, or something happening
No,
there?
so there's like this Raspberry, where was it, about like slide
Yeah, the
45
Pi
maybe?
2 or Pico 2, right?
Yeah.
Yeah.
Um, so there's so you have like this Raspberry Pi that says like via USB you send it a command to, so the switch is down here, this little switch,
Oh, I see.
this little chip.
Uh-huh.
So you tell there's some software that sends a command to the Raspberry Pi that then pulls a pin and switches this switch. So there's like no mechanical switching or anything. You could completely automate that and run that in a quite quickly. So it's just like, for the demo, we slowed it down a bit artificially, I would say. So you could switch this in like on the order of milliseconds or something. If you get your timing right, then you can be quite quick with this kind of attacks.
Okay, very interesting. Like closing thoughts in terms of we have a next door in our state, we have a $7 billion data center. We have a lot of data centers getting attention here because North Dakota is cool. It's very cold, right? And then and energy is low for now, I guess, cost wise. But I think what is your perspectives of as data centers are growing and what there is a lot of cloud, the CI/CD pipeline. Of course, these servers are running everything mostly on cloud nowadays, unless there are some critical infrastructures. They have a dedicated server. What are the couple of things or research problems that a lot of students are listening, and
Mhm.
looking at the from the data center perspective, how if you're working on a data center research, what could be you're seeing, in terms of that people can chew on as we for dissertation topics.
So I think you can go into the detail of certain things. So that is one. So you can just like pick any these center systems. They are not as scrutinized as many people would think, right? Especially at the lower hardware level. So often there are like a few people who develop a server motherboard or something, and it's not as well scrutinized as, let's say, an Intel CPU that thousands of researchers have looked at. So if you start to, I didn't talk about this, but if you start to look at this, the server hardware, there are lots of interesting things that you can find still, I think. And they run like these extra chips that are always on, etc. You can also look at a much higher perspective. So you can look at the data center and everything around it. So for instance, to give an example, there's like quite a famous case, I think, where a data center operator had to change the way they schedule processes to not bring down the power grid next to the data center. Because what they were doing is like it was completely idle, and then they allocated a job to all the nodes, and all the nodes go to full load, right? So
Yeah.
that is not what a grid likes, right? The gas turbine or whatever needs a few minutes to spin up. So you have like the sequencing that you need, and that also creates like interesting questions. What if somebody controls like part of the data center? Can they do some shenanigans and get the grid down or something? So you can also look at the as a whole system essentially and understand what kind of attack surface exists in that and what you can do about it.
Cool. I think I learned a lot today. Thank you so much, Dr. David. Appreciate for spending your time with us. You will receive a nice plaque and a letter from our dean for appreciating your time. And hopefully we can continue our collaboration. Maybe we could talk, or maybe we could do some proposal and come to our
Sure.
conference in a few this year or maybe next year. We think, it'd be nice to get to do something interesting collaboratively, and I'm going to learn more
Yeah,
about
sure.
what this UK and UK have and some cyber center, a national center. I think I'm going to
It's
Singapore
see.
next week for their summit, but I think we'll figure out a way to collaborate with you. Thank you so much.
Good. Have a nice rest of the day and have a nice weekend then. And yeah, we'll stay in touch.
Take care.
Bye.